Good morning to everyone. Today I am going to represent the topic PWM inverters, which stands for pulse width modulation inverters. PWM inverters are one of the most important power electronic converters used in renewable energy systems, motor drives, UPS systems, and electric vehicles. The main function of a PWM inverter is to convert a DC power into AC power while maintaining good waveform quality. Unlike conventional square wave inverters, PWM inverters can produce an output waveform that closely resembles a sinusoidal waveform. This reduces harmonics, improves efficiency, and enhances overall power quality. In this presentation, we will discuss the need for PWM inverters, their working principle, different PWM techniques, advantages and applications. What is a PWM inverter? PWM stands for pulse width modulation. A PWM inverter converts DC electrical power into AC electrical power by controlling the width of switching pulses. Instead of providing a fixed width pulse, the inverter continuously varies the pulse width according to the desired output voltage. By adjusting the on and off duration of power electronic switches, the inverter can control both the magnitude and quality of the output voltage. The resulting AC waveform becomes much closer to a sinusoidal waveform, which is desirable for most electrical loads. Therefore, PWM inverters are widely preferred in modern power electronics applications. PWM inverters are needed because conventional inverters generate square wave outputs that contain a large amount of harmonic distortion. These harmonics can cause heating, losses, and poor performance in electrical equipment. PWM techniques help reduce these harmonics significantly. Another important reason is voltage control. PWM allows smooth control of output voltage without requiring additional hardware. It also improves efficiency by minimizing power losses. Furthermore, PWM inverters provide better power quality and are highly suitable for variable speed motor drive applications. Because of these advantages, PWM technology has become the standard method in modern inverter systems. How PWM inverter works? The working of a PWM inverter is quite simple. First, a DC voltage source such as a battery, solar panel or rectifier provides the input power. The inverter contains power electronic switches such as MOSFET or IGBTs. The PWM converter generates switching pulses and sends them to these switches. The switches turn on and off at a very high frequency. The pulse widths are varied according to a reference signal. Wider pulses correspond to higher output voltage, while narrower pulses correspond to lower output voltage. After switching, the output contains high frequency components. These unwanted harmonics are removed using filters, resulting in an AC output waveform that is very close to a sine wave. Thus, PWM enables efficient and controlled DC to AC conversion. Single pulse width modulation is the simplest PWM technique. In this method, only one pulse is generated during each half cycle of the output waveform. The width of this pulse is varied to control the RMS value of the output voltage. Since only one pulse is used, the circuit is simple and easy to implement. It also requires less control complexity. However, the major drawback is that the output waveform contains a significant amount of harmonics. Because of this limitation, single pulse width modulation is generally used only in low power or less demanding applications where waveform quality is not a major concern. Multiple pulse width modulation improves upon single pulse width modulation by generating several pulses during each half cycle. Instead of using one wide pulse, multiple smaller pulses are distributed throughout the cycle. This arrangement helps reduce harmonic distortion and improves the quality of the output waveform. As the number of pulses increases, the output waveform becomes closer to a sine wave. The main advantage of this technique is lower distortion and better performance. However, it requires more switching operations and a slightly more complex control circuit. Even, even though it provides a significant improvement over single pulse width modulation. Sinusoidal pulse width modulation, commonly called SPWM, is the most widely used PWM technique. In SPWM, a sinusoidal reference signal is compared with a high frequency triangular carrier signal. Whenever the sine wave is greater than the carrier wave, the switch is turned on. When the sine wave is less than the carrier wave, the switch is turned off. This comparison generates pulses with varying widths that follow the shape of a sine wave. As a result, the output waveform closely resembles a sinusoidal waveform. The SPWM offers low total harmonic distortion, better voltage control, and excellent performance. Because of this benefit, it is widely used in industrial motor drives, solar inverters, and UPS systems. PWM inverters offer several advantages. They provide low harmonic distortion, resulting in improved waveform quality. They have high efficiency because switching devices operate with low power loss. PWM also allows precise control of output voltage and frequency. Another benefit is the reduced size of filters required to smooth off output waveform. Due to these advantages, PWM inverters are used in many applications such as UPS systems, AC motor drives, solar photovoltaic systems, electric vehicles, renewable energy systems, and industry automation. Their flexibility and efficiency make them an essential component in modern power electronics. Thank you for our patient in listening. I hope this presentation has provided a clear understanding of PWM inverters and their importance in renewable energy and power electronic systems. Uh, Thank you all.